circuits. And we were talking about pipelining, where the problem was latency. However, after having a certain stages of latency, the output is actually continuous. So that way, it's a good technique. It's also used in many places to achieve the high speed. And we have talked about okay, we have talked about this particular diagram, where we also understand that if you are implementing uh, instead of pass transistor, if you are using a transmission gate or some other things where you are not using the non-overlapping clocks, then such things can happen, which we are calling it as a race around problem. So if clock and clock bar having a clock skew, both are 0 or both are 1, such things will happen. So what we used to do till now, if there is a something like clock skew like this, so one of the solution is the non-overlapping one. You can make the clock such a way that it's non-overlapping one. You can do that, there is no problem. However, if you are using the transmission gate over here to get the correct output every time, right? So in that case, what is going to happen, one of the transistor is going to be on, and that will create a problem. Or you can say that input is actually visible at the output, and it's known as the Racearound condition. So in such cases, we also studied one of the popular thing, which is known as the C-square MOS latch, which looks like as follows. We understood the functionality, how it works in previous one itself, that this is clock bar, and other stages are also required. So this is one of the latch which we have studied already. So if this is D input, next might be, let's assume that f is the function f which you want to evaluate. It might be static, it might be dynamic. Let's assume that it's a static function, or the static CMOS gate based combinational based circuit. So in that case, you can avoid the whole thing which we are using over here, and we can implement this one with the C-square MOS latch. Here also, like, you can implement the whole thing with, okay, this is the third stage. Second stage, again, you can implement it with C-square MOS latch, and each stage you can have C-square MOS latch, and in between you can use it. So as we have studied, if you want to have the NOR Racearound condition, it's known as the NORA CMOS logic, where it's going to be useful for the pipeline structure or the cascading of the structure. So when you are cascading the functions which are running on different clocks, I would say that different clock phases or different clocks, then this pipeline is going to be activated, and this pipeline structure is going to give us advantage in terms of the speed. Or you can say that you can divide the speed wherever it's required on the basis of the number of stages. So this is very popular thing. However, okay, before going to this, there might be a problem. If you remember, when we were talking about the different cascade of the stages in the combinational logic, if you remember, we have studied the last topic of the combinational logic, where you are changing like first gate was connected with the second gate and second gate was connected to third gate and so on. So when you were doing this, there were some problems in terms of I would say that the output, right? And we solve that using domino logic, where what we have done, we have checked that whether it's power up device or the power down device which you are using. If it is power up, you made that if this is going from 0 to 1, here also like all the inputs, like here also it has to be 0 to 1, and for that we have implemented one inverter in between. This was one thing. Other than that, we also implemented that if this is power up network, which is connected with n CMOS domino logic, and another way is p CMOS domino logic, right? So alternate of these is going to solve the problem of the domino logic. Because of such problem, like that problem was there. So now let's see that if it is a pipeline structure, whether it's going to give you same problem or not. Here I gave the solution in this, but before going to solution, let's look at the problem. Let's assume that all these are C-square MOS latches, right? Which is already known to us. This is also C-square MOS latch. And of course, the capacitor is the parasitic capacitor available at each of the node. And you can see if the first stage is this one, as it is pipeline, first stage is working at 5, or let's make it this way. If it is working at clock, this one is at clock bar, and this one is at clock, right? Alternatively, like you do that. So what is going to happen? Let's see. So let's start from the first fact that we are going to have clock equal to 0. So if clock equal to 0, this transistor is on, clock equal to 0. Sorry, clock bar equal to 0, I would say that. Then I made a mistake over here. If clock equal to 1 and clock bar equal to 0, then both the transistors are going to be on, right? Whereas in this case, both the transistors are off, right? And if you look at the last one, they are on. So when these two are on, whatever the input is here, input is 0, then this is VDD. If input equal to 1, then this side, it's going to be equal to 0, right? Depending on the switches. Now, the problem occurs over here. Okay, no, in this case, not a problem. But the problem occurs when we are going to make sure that clock and clock bar has overlap, because that is the reason why we have implemented C-square MOS latch. So let's assume that there is 0, 0 overlap. Means clock bar also equal to 0 and clock also equal to 0. You see, all these up transistors are going to be on and other transistors are going to be off. Now things are depending on now input. So now if input equal to 0, the output is VDD. If input equal to 1, output equal to ground. So it's an inverter, right? This is acting as an inverter only. But what if this guy is equal to 0? If this is 0, then this is again VDD. And if by chance G equal to 0, then again this is equal to VDD. So it's all about what value of function is giving the output. and whether this node is dynamically changing its value from VDD to ground or not, that is going to create a problem. And note that if it is 0, it's a problem because it's going to make connection directly to VDD over here. So here also it's VDD. So it doesn't matter this one. If this is 0, it's a problem. And that is what I have written over here, that a C-square MOS based pipeline circuit is race free as long as all logic functions F and even G between the latches are non-inverting. If they are inverting, which is the case for 0, 0, then it creates a problem. Otherwise, there is no problem. Now let's see one example where that function is an inverter. F is actually an inverter. And I am talking about a situation when there is a 0, 0 overlap. Let's start with 0, 0. If it is 0, 0, then all these transistors which I made here are going to be on. Now look at this. When input equal to 0, VDD is available here, right? VDD will make this transistor on, and this is available at 0. 0 will make this transistor again on, right? And the output is equal to VDD. You see? So if it is 0, 0, if it is 1, 1, what is going to happen? Let's see that. In the same circuit, we can check what is going to happen if it is 1, 1. In the case of 1, 1, this transistor is going to be on, this is on, and we have to see for, okay, clock, okay, 1. So this is also 1, right? So here, when input equal to, let's say 0, then this is VDD. If this is VDD, already this is 0, and this is available at output. And similarly, if this is equal to 1, this transistor, below transistor, is going to be on, output is equal to 0, 0, and this is again, because of this one, this is off and other side is on, and output is VDD, and because of this VDD, this transistor is on and output is 0. Notably, what we are doing is we are checking whether there is a direct path from input to output or not. Actually, when we are doing this pipeline, we don't want anything going beyond this. The first stage, okay, sorry, it has to be here. When clock is high, only the first stage should give the output. Second stage should not be affected from the previous output. So we don't want that. So 0, 0 or 1, 1 or any overlap is going to be there. It's going to give you the direct connection between input and output, whether it is inverted one or the non-inverted one, it's going to be there, right? So let's revisit what we have written. We are saying that C-square MOS based pipeline structure is race-free until it's non-inverting. If it is inverting, then all these problems are, if it's inverting, all the problems will occur, because whenever it's 0, the output is VDD. It does not matter. And we are talking on overlap, right? So such things will happen. So what we are saying, this is one of the technique, like we used to do it in domino logic. If you remember, in domino logic, what we were doing, we were adding first stage with, if it is with PDN, next stage is going with the power up network, and later on you have the C-square MOS latch. In this way, we make sure that there is not requirement of any inverter. So the first solution was in the domino, we were using the inverters in between, and we make sure that the transition of the input is going from only and only from 0 to 1. We were we were doing that, right? So here also we have to make sure that, like dominoes, which we are doing, one was using inverters in between stages and giving proper input pattern. So input pattern was already defined, going from 0 to 1 or 1 to 0, depending on what logic you are using. And you can use alternate that with PDN devices and PUN device, which is known as NCMOS logic or maybe PCMOS logic, right? So in that way, you can use this one where there are two different modules. One is called clock module. These two are just for an example, but how does it they look like when there is clock and clock bar modules are there. In NORA CMOS modules, there are different phases of operation. When it's a clock module, during clock equal to 1, if it is clock module, it has to evaluate. So during clock, it's going to evaluate. In clock bar module, when clock equal to 0, it's going to evaluate. However, in other phases, it's going to be precharge and hold. The logic is going to precharge, and wherever the latches are there, they are going to hold the previous value. So this is what we can design it with no Racearound condition based CMOS module, and you can use C-square MOS latch, and you can give the proper input, right, going from 0 to 1 or 1 to 0, depending on what you are doing. So what design rule says that the dynamic logic rule says that inputs to a dynamic clock N or clock P blocks are allowed only from 0 to 1 or 1 to 0 transition during the evaluation. If it is different, look, if it is going from 0 to 1, it's when it's a clock N, what is going to happen? It's not, output is not going to be recharged. And same thing will happen if it is flipped logic. So it's all about how you are using clock N and clock P. It's referring with the NCMOS and PCMOS logic also. This is true for that also. Either you use it PDN and PUN. So accordingly, you can find out the new combinational logic diagram, and then you can give the input accordingly. And of course, the C-square MOS rule. This is actually a latch which is going to be kept in between different functions. Like if there are many functions are there, F1, F2, F3, I'm doing it, and then before this I should have the latch in between every input and output. You should have latch. This was the concept of pipelining. Note that if this is working at 5, this is working at, like, every 0 to 1 transition. So first stage is going to work when 0 to 1 transition is for the first stage, second one 0 to 1 for second, and so on, right? So this is what we did it. So to avoid races, the number of static inversions, so in between this, after latch, you need to add actually different inverters, as we already know that why we require it, right? If you are in clock N, and if there is no transition going from 0 to 1, it's better that add one inversion. And in clock P, if there is no inversion is going on, then add accordingly the number of the inverters. So if there is a static inversion is there, then you should use even number of inverters. This is going to act as a driver also, or you can avoid it if you don't want to use it. Even is as good as nothing, right? It's like a buffer. But if there is static inversion is not happening, or the particular node is acting as a dynamic node. When I'm saying dynamic, it's changing from 1 to 0, 0 to 1 transition, as it was happening here. So that node is actually reverse of what you are expecting. Then you need only one inverter, right? So that is what written here, and it says that the revised C-square MOS rule for the no racearound condition says that if there is only one transition, you make sure that if it is as required going from 0 to 1, then you require one inverter. But if this is not going this way, but if it is going this way, you know that, then you are going to use two inverters or maybe no inverters. That will also work fine. So that is what the hand rule over here. The thumb rule says that the number of static inversion between C-square MOS latches should be even in the absence of dynamic nodes, means what I told just now. And if those things are present, inverters between these latches has to be odd. So that went to the next page. So okay, so this was about all the scheme for the sequential circuit which we have studied, right? Yeah.
Sir, in the previous slide, sir, in order to avoid resist number of static inversion between CMOS, latches should be one. Now, previously we have written that if suppose the logic function which we have implemented.
Actually, latch has also one inversion, right? Latch is itself is one inverter.
Suppose if there is no latches and we are implementing a logic function, and if it is
then it's not a NORA CMOS. NORA CMOS is the one which is avoiding the situation when the 0 0 or 1 1 overlap. For avoiding this, we are using C-square MOS latch. This is the solution when it's a pipeline, right? Okay, so we can start from maybe how the problem was originated. We could have done this one with just sample, hold, and next function. But the problem was when there is overlap, means this is also one and this is also one. What is going to happen? This is going to be all are on. I don't want that. I wanted each one of the stage working on next phase. This has to work in the first clock phase only, going from 0 to 1. This has to work in the second clock phase, right? When it's going from 0 to 1. Otherwise, this guy is going to disturb this node, and this node is going to disturb this node, and this node is going to disturb this node, and output also. We want to stop them. So what we have done, we have used the technique known as the C-square MOS latch. So if you remember, I gave you different options also. One of them is use a non-overlapping clocks. If they are like this, no problem. So there is 0 0 overlap is there, right? 0 0 overlap is there, no problem. But during the 0 0 time, it's going to latch the previous output, right? It's off. Everything is off. So wherever they are, they will be there only, right? So that's why you are taking C-square MOS latch, and then you are doing all these things. And C-square MOS is itself is an inverter. There is one inverter already which is working at the clock. Okay, right? So any other doubt? I believe no doubt this is similar to what domino logic is there. So domino logic has been extended to sequential circuits, which is known as no racearound condition or the NORA CMOS logic. Okay, if you don't have any doubt, then it's end of the sequential circuits, whole circuits. But the important topic which is left, which is the last topic of this particular chapter, which is generation of the clock. So we require everywhere different clock, but this clock was available, and then clock was actually made it as a non-overlapping clock like this. Right? We did all these things, but how to get the actual clock? In general, like you need something called oscillators. although it's a big topic and it's a topic of maybe the analog circuit design, where oscillator does not work alone as a clock, but you need a system called phase lock loop, which is going to give you the stable clock with the required phase noise. Anyway, but this oscillator can be designed many ways, which is actually part of this particular chapter, and it's given in Rabe book. So for the completeness, I am doing it. So oscillator, sometimes known as the multivibrators, has three different kind of multivibrators. One is called bistable multivibrator. Another one is astable multivibrator, and last one is the monostable. I should have written opposite way. By the way, monostable is also known as one shot or sometimes mono shot. All names are synonyms to each other. Right? So bistable multivibrator are the one where there are two different stable points are there, logic 1 and logic 0. If the output looks like this one, it's a bistable multivibrator, right? Notably, this requires input. Or you are, when I'm saying input does not mean that VDD and ground. Of course, all these circuits requires VDD and ground. VDD and ground without power supply, these circuits does not work. Okay, so all these circuits require VDD and ground, but this circuit requires some input, like the non-overlapping clock, which we have done it very recently. This is also a bistable multivibrator. Look at this. This is also a bistable multivibrator where there is an input, which is clock, right? But there might be another class where input is there, but output is just one shot like this, or the creation of the pulse. If you remember, we have done such kind of circuit previously, some delays there. If it is like this, so XOR gate is the one where both the inputs are different, then output is one. So if I am doing this one, the output here is actually delayed version of, so input was here, but because of delay of this TD element, the output is after some time like this. So in that case, this particular window is going to be the output. So this is called mono shot or the one shot or monostable, which requires input. Look at this, input is there. It's not in the absence of input. Input is there here also. But astable multivibrator is the one which is going to have VDD and ground, but does not have any input. Right? You must have designed like LC oscillator or many other oscillators are there where you don't require any input, right? So that kind of oscillator is important for us. But for the digital oscillator, let's start with the first thing, which is known as the Schmitt trigger. First of all, if you remember, Schmitt trigger is the one which uses the hysteresis, right? You know about hysteresis, I believe that. Hysteresis is the one which remembers the value and the path when you are going is different, and when you are coming back is different. By the way, input is V in and output is V out, right? So something like this is actually the Schmitt trigger. But same thing, you must have used it in many places, not only here, but many places. Let's assume that it's a comparator. In comparator also you must have used it. Like this one. I'm going a bit away from digital, but still it's a digital. Let's assume that I have designed a circuit which is an operational amplifier like this. This is also known as zero crossing detector, right? So when input is crossing from 0, below 0 and above 0, the output is actually 1 and 0, right? You must have seen it. But if you are using such a system, it's not a good option for making the comparator. What do you think, Nandit? Why it's not a good option? Okay, if this comparator is look like this one. You must have studied this thing in previous course. That's why I'm asking. The mixed signal course. Comparator you studied it. So why, like, this is not a good option. Others can also give the answer if you want to give. If somebody knows the answer, you can try at least. Okay, only seven are there. So Nishant, do you know Nishant or other people?
Sorry, sir. No idea.
But you understand what my question is, right? Do you understand
Yes,
my
sir.
question? This is very important. Look, the problem here, let's assume that my input does not look like this one. My input look like as follows. Look at this. This is interesting input I am going to give. Right? You must have seen such kind of input on oscilloscope, the real. So how the output will look like? So now do you remember, Nandit? Right? You agree with me, right? So this output will be there, but I don't want to see this. I know that this is some kind of noise or some wrong values. What I can do in that case? The easiest thing is, I know that what is the range of input noise, I should say that. If I know that where is the range of input noise, instead of zero crossing detector, I'm going to make two different points where it's going to make a decision. So there are 2 points. Instead of one point which was here, which I was calling it VM or the switching threshold, instead of that, I'm moving that one upside and one little bit downside. And this is the range which I know that what is the input noise range. If it is there, then look, this is going to be treated as, if it is coming from 0, then it's 0 only. For qualifying that as a logic 1, it has to go above VM plus. Let's revisit what we have drawn over here. So there are 2 inputs, right? One is known as, let's call this one as VM minus and this one is VM plus. So if my input is more than VM plus only, not this one. If you remember, the comparator has this characteristic also. So it's hard number over here. But instead of that, I moved this number little with this side and this number little with this side. And this becomes the S curve, right? Or the hysteresis curve, which can remember its usage is not only that when you are going, you are taking different path, and when you are coming back, you are taking different path, but it's all about the switching points are different. these two are the switching points. Right? Note that whenever you have made Schmitt trigger till now, you made the positive feedback, right? I'm taking a little bit about op-amp. If you remember, this circuit is a positive feedback. Right? Yeah, Nandit, what do you say? Right? This one is a positive feedback, and notably, the output is not minus R1 by R2. Right? The output is actually going to be either logic 1 or logic 0, or you can say that it's going to be rail to rail, right? Because of its positive feedback, and inherently this entire scheme is going to make sure that it's going to have this kind of characteristic, and you are designing these 2 points where it's going to flip the value, right? So same thing I can do it when it's a Schmitt trigger. Either you take this one, or as I told you, use something where it's a positive feedback. So where we are using this positive feedback, let's assume that I'm having a circuit which looks like this one. Look at this. This is in plus, this must be in minus, and let's assume that this is some current as a load. Sorry, not in minus, this is out minus. Similarly, I might have another circuit exactly identical to that, which is in minus, whose output is out plus. If I want to make the positive feedback, what I can do, there are 2 things. Like extension of this circuit is the last topic, but I can do this one also. This becomes a positive feedback. Notably, if you draw this one more time, it's cross-coupled latch, right? So this circuit is also known as latch circuit, because it's going to latch. It's not going to oscillate because there are 2 stages, and if you are interested at particular clock, use clock. And if you remember, if you are going to do this one, this is alone is not going to help you to get a better output. So what you can do, you can make this one as NMOS, and again you make like complete an inverter. If you remember the sense amplifier, right? So use sense amplifier, and sense amplifier is same one. And if you want to make not the latch, if you want to make this one as resistor, you can connect here one transistor, which is going to make sure that it's going to be give you output when clock is transition from 0 to 1, right? So let's have all these things clear in our mind that Schmitt trigger is going to remember, and it's not going to be just a zero crossing detector or the midpoint value detector. Or you can say that, look, if there is an inverter, by the way, this is one of my PhD students' work using which he made the very fast comparator, that inverter as a comparator. I suggest you can read his papers. So his name is Dinesh Kumar B. He is one of my TA also, right? So he's what he is doing, the inverter, if it is rightly sized. When I'm saying rightly sized, means the upper portion's resistance, means PMOS resistance, is equal to the NMOS resistance. In that case, both are equal. Means if I am changing the input, which is going from 0 volt to, let's say this is 1 volt, if I am changing from 0 to 1 volt in a ramp, if I'm going to give, the output is going to flip at 0.5, right? So what exactly this does, this compares So if I'm whatever input I'm giving, it compares that with the 0.5 volt, whether it's upside of 0.5 or below of 0.5. If it is more than 0.5, logic 1 is the output. If it is less than 0.5, logic 0 is the output. Similar to what we were doing in the zero crossing detector, right? Where this is connected to 0.5 volt, this is 1 volt, this is 0. I'm changing the input. If input is more than 0.5 volt, the output is logic 1. And if it is less than 0, less than 0.5, output is 0, right? So this was very quick observation, and using that you can make a system which is going to be act as a comparator, right? So using all this, let's look what Rabe's book is saying. So it's a circuit where sequential element. This is a the latch, which is also the sibling of the resistor. The most important property of such a circuit is that it has two stable states, and hence known as the bistable, as we know. The bistable element is not only the sequential circuits of interest, other regenerative circuits. Notably, whenever you are seeing this word regenerative, means it's a positive feedback, because it regenerates itself, right? Can be cataloged as stable and monostable, which we already talked about, and there are many techniques. But interesting thing is Schmitt trigger, which remembers the thing, and it has two different switching thresholds, not only one. So the definition wise, Schmitt trigger is a device with two important properties in terms of digital aspects. So it responds to slowly changing input waveform with a fast transition time. So it's very fast output because it's a positive feedback. Positive feedback is quite fast, right, compared to negative feedback. Negative feedback takes time, but it's settled. Positive feedback is not going to stable at one point, but if it is finding out the stable points, either logic 0 or logic 1, then it's going to be staying there until the inputs are not changing, right? So the second property says that the voltage transfer characteristic, which is VTC of the device, displays different switching thresholds, means positive and negative, like the case the two switchings are there, V plus, Vm plus, and Vm minus. Unlike the case of the normal inverter, which does not remember or does not have the hysteresis, and it's going to be hard value of Vm, right? So these things we are going to achieve with the fact that we know how to tune noise margin high and noise margin low. This is going to be advantageous in that way. We are going to use it, and we are going to understand how it's happening. Okay, so let's understand this particular device as a Schmitt trigger based non-inverting Schmitt trigger. By the way, this is not an inverter. It might have two inverters back to back. Inside this particular thing, you might have two inverters back to back, but I have designed such a way that the switching threshold voltage is not Vm. It's not exactly the midpoint Vm, but it's like this, as it has been shown over here, so that Vm plus and Vm minus will be there, right? So as I already explained, it suppresses the noise. So if the input looks like this one, and you have two switching thresholds, Vm plus and Vm minus, unlike the case when you had only switching threshold Vm, if it is a normal inverter, the output would have been different, or output would have been look like as follows. Let's assume that it's two inverters back to back. In that case, output may have looked like this one, right? But note that it's an illusion. This particular thing is getting settled and the output would have been now settled like this. So this was the original input, but because of this fluctuations, which was actually the settling time, I don't want to take that one also in my output. Means if there is small amount of noise, that is noise will be amplified, because common source amplifier or the class AB push pull amplifier, that's the characteristic of my inverter. So if I am around switching threshold voltage, that was the last example of your first assignment, where I ask you to do this, where you have given VDD by 2 and you have given some small input that was inverted and getting amplified. So here also, like, small input can get like amplified and it's act as a large signal. So when I'm using two switching thresholds, the output will look like flat logic 0 to logic 1, because you have two switching threshold. I'm drawing it for you people. See? So after the switching threshold only, it's getting the output, and this is going to be driven by the propagation delay of this comparator or the whole circuit. Where is it now?